last time we were together, we learned that you can evaluate limits using direct substitution. So for this problem, we want to find the limit as x approaches 2, so we can substitute 2 in for each of our x's here and evaluate. But when you do that, you find that this ends up equaling 0 over 0. Now this poses a problem because we have one rule that tells us 0 divided by anything will be 0. But another rule says any number divided by 0 will be undefined. So which one is supposed to apply here? Well, actually, neither of them does. This is referred to as the indeterminate form. We don't know what it means, and we are not able to evaluate this function using direct substitution. So we need a different method. So what we need to do for this problem is to factor the numerator. So this becomes the limit as x approaches 2 of x plus 4 times x minus 2 all over x minus 2. Now we can see that we have matching factors on the top and the bottom, so that x minus 2's divide out. Now this becomes the limit as x approaches 2 of x plus 4. Now x plus 4 is one of the functions that we know direct substitution will work. So we could substitute the 2 in for x plus 4 and see that our limit equals 6. So in order for this to happen, we had to divide out those x minus 2's. So this is referred to as the dividing out technique. So one clue you need to do this is you have the indeterminate form 0 over 0. Also you have a polynomial on the top or bottom or both. And this is what happens. So I'm going to give you another one to try. I want you to push pause, try it, and then go ahead and resume and see if you did it correctly. So go ahead and try this problem. The factoring here is a little tougher because we have 4 terms instead of our normal 3. So we're going to factor this one by grouping. So we could group the first 2 together and the second 2 together. Notice that this was an addition, so I'm allowed to do that. If that was a subtraction, I'd have to include that with the 2. So we take out our greatest common factor from the first piece, which is an x squared. So x squared times x minus 2. Then take out your greatest common factor from the second piece, which is a 2, leaving you with x minus 2. Now for both of these pieces, that x minus 2 is the GCF. So we could factor that out, which gives us an x minus 2 and leaves behind x squared plus 2. So this is the factored form of our polynomial that we have in the denominator. So going back to the original problem, this is the limit as x approaches 2 of x minus 2 over x minus 2 times x squared plus 4. We have our x minus 2 and x minus 2 divide out. So the limit as x approaches 2 of 1 over x squared plus 4. Now that we've divided out, we could try direct substitution again. 1 over 2 squared plus 4 gives us an answer of 1/8. Now something else I want to point out here. Remember, as you get into calculus, writing things neatly, keeping track of your work is very, very important. So each step of the way here, I wrote the limit and the limit because I had not used that yet. But now at this point, I've actually evaluated the limit, so I don't write it anymore. So pay attention to those things. Don't get lazy with your writing. Okay, let's try another problem. So this time, let's look at the limit as x approaches 0 of the square root of x plus 9 minus 3 over x. Again, you want to start by trying direct substitution because a lot of times that works. It makes our life easy. So if we substitute the 0 in, we would get the square root of 0 plus 9 minus 3 over 0, square root of 9 minus 3, things are not looking good, 3 minus 3 over 0, yep, indeterminate form. So that doesn't tell us anything about the limit. Maybe it exists, maybe it doesn't exist. We're going to have to do some work to figure it out. The last two we use the dividing out technique, but here there is no polynomial for us to factor, so we need something new. This problem has a radical in the numerator, so we're going to use what is known as the rationalizing technique. Now, you know, if I was to give your problem like 3 over the square root of 5, we're not allowed to have a radical in the denominator, so we would multiply the top and bottom by the square root of 5 and have an equivalent fraction just written in a different form. We're going to do something similar here, but this time the radical's in the numerator, so we're going to rationalize the numerator. In order to do that, we need to multiply the top and the bottom by the conjugate of the numerator. So remember, to do the conjugate, this middle symbol becomes the opposite. So we're going to multiply by the square root of x plus 9 plus 3 over the square root of x plus 9 plus 3. This way, we're not changing the fraction, we're multiplying by 1, so it stays as an equivalent fraction. So now we have the limit as x approaches 0. Okay, so on the top here, we need to FOIL. So we're going to multiply our first two terms together and get x plus 9. Then our outside two together, 3 square root of x plus 9. The inside two, I just realized I rewrote the problem and I wrote it down wrong. Not sure if you noticed that. That's supposed to be minus. Sorry about that. So this one is minus. And now here we have plus 3 square root of x plus 9. And then our last two terms, minus 9. On the denominator, let's just don't distribute the x. So square root of x plus 9 plus 3. Now you need to simplify the numerator. So here we have a negative and a positive of the same term, so that's going to subtract and make 0. So we have the limit as x approaches 0 of x plus 9 minus 9. Combine like terms again, there we have a 0. So we've now rationalized the numerator. That radical is not there anymore. Now it's moved to the bottom. But the important part is that on the top and on the bottom, we have a matching factor of x, and those can divide out. So now we have the limit as x approaches 0. Since we divided them, we have 1 in the numerator. And we've divided out, so hopefully direct substitution will work now. So I don't need to write limit anymore. I'm actually evaluating the limit. I have 1 over the square root 0 plus 9 plus 3, which will be 1 over 6, and we're able to get our answer. I'm not going to go through another example of one of these here, but if you would like to see another one, take a look in our textbook. Most of these work the same. You just need to remember the main step was right here in the very beginning where we multiplied by the conjugate in order to get rid of the radical. Okay, next problem. Oh boy. So the limit as x approaches 0 of this complex fraction. It's called a complex fraction because you have smaller fractions within it. So our first technique was the dividing out technique. Well, there's nothing to factor here. That's not going to work. Our second technique was rationalizing. Well, no radicals, so we can't rationalize. So our third technique that we're going to learn here, let's call it fraction busters. I know it's a silly phrase, you might have used it in middle school, but essentially here we need to eliminate these complex fractions in order to find our limit. So what we're going to do is multiply the numerator and the denominator of our big fraction by the least common denominator of all of the smaller fractions. So we're going to multiply by the LCD of all the mini fractions. So depending on the problem, you might have 1, 2, even 3 fractions within. In this one we have our 2 that are on the top here and here. So our least common denominator is going to be 4 times x plus 4 because we have 2 separate fractions, you multiply their denominators together. Okay, so we're going to multiply by that LCD on the top and on the bottom. So in the numerator, remember that all of this is being multiplied. So we need to take this piece and distribute it to each of these fractions. I'm probably going to show more work here than you eventually will need to. I want to make sure it's really clear what's happening. So 4 times x plus 4 over x plus 4 for that first fraction minus 4 times x plus 4 all over 4 for the second fraction. And then on the bottom, no fractions. So x times 4, x plus 4. Now what's nice about this, and here's why we call it fraction busters, each of those mini fractions should divide out. So in our first one, x plus 4 and the x plus 4 divide out. In the second one, the 4 and the 4 divide out. If that does not happen, that means you probably made a mistake. So check your LCD, make sure you wrote it out correctly. We're left with 4 minus x plus 4 all over x times 4, x plus 4. Now I know both of those x plus 4's are in parentheses, but do not be tempted to do this. Remember, we don't cancel out, we only divide out. And this x plus 4 in the numerator is being subtracted, so you are not allowed to divide both of those out. Instead, we need to simplify our numerator. So we have the limit as x approaches 0, distribute that negative inside here. So excuse me, I'm running out of space. I'm going to try to squeeze it in. So on the top we have and now again at this point an x in the numerator and x in the denominator divide out. So we have the limit as x approaches 0 of -1 over 4 times x plus 4. Then we could do direct substitution, substitute in the 0, and we end up with -1 over 16. And we were able to evaluate our limit using the fraction buster technique. We have one final problem to look at. The limit as x approaches 0 of 1 minus cosine of 0 over 0. So start off, try direct substitution. we would get 1 minus the cosine of 0 divided by 0. Our cosine of 0 is 1. Should have guessed. Indeterminate form. So we do not know this. Remember, indeterminate form does not automatically mean that the limit does not exist. It just means direct substitution did not work for us. Dividing out technique, not going to work. Rationalizing technique, not going to work. Fraction busters, no fractions, not going to work. So of those new methods we've learned, none of them really apply to this problem. So what we would do in this case is we would actually do what we started with limits. We would either use our graphing calculator to make the graph or look at the table and use one of those two situations in order to evaluate it. So I'm not actually going to do this problem here, but I wanted to mention if nothing else works, you go to your calculator, you look at the function, and you use that to evaluate your limit. And for now, that is it. There's a little bit more to section 12.2, but that will be another lesson.